All right, hi. I guess we can start. Yeah, hi Farhan. Nice of you to join. Is that Pico capture up and running? No, unfortunately not. I can show you how it looks. So it's all fake. No, not fake, but I have a webcam that films a screen. So it is it is what it is. The Pico capture stuff I put on the shelf for now. And I want to focus on the actual cart for today. Yeah, so I guess I can do like a recap of what's been going on since last stream. So yeah, I got the PCBs. And I soldered up a couple of them. And so on the N64 that you can see here in the video, I've changed the flash to 16 megabytes instead of 8. I did that just now a couple of minutes ago, and it works. So the thing is that the Super Mario 64, hello WebHDX. The thing is that the Super Mario 64 is 8 megabytes large, and we need sort of all of the ROM, the beginning and start. The beginning and end, because in the end there's some checksum and stuff. So we need either to execute from RAM or have a little bit larger flash. So I went with the 16 megabyte of flash. So the firmware takes up like a couple of kilobytes, and then there's the ROM. Yeah, so it boots. It works every time. So just to show you, I can turn off the N64, turn it on again. And in a few seconds, it's gonna start again. Yeah, there we go. So the truth is that the very first revision with the flying wires was kind of unstable. Yeah, nothing fake about booting code from your own code. No, exactly. So I just wanted to show, I turn off the N64 and I turn it off on again, and it boots. And the funny thing is that you can see this kind of blue light. The stamp has a LED connected to the CIC clock. So whenever, yeah, it should be desoldered, I guess. Or I think there's a jumper or a solder bridge that I can cut. I just haven't cut it. But it looks kind of cool that it's a blue light. Just to show you, I turn off the N64 and I power cycle the Pico. And then I turn on the N64. You can see it lights up. It's just an artifact, and fortunately it is on the CIC clock signal, which is kind of slow, so it really doesn't matter, and it doesn't affect the system in any way. It just, yeah, looks annoying, I guess, but it also looks kind of fun. Yeah, so I guess I can switch screen to this one. Yeah, so I set up my DSLR camera, and this time I pipe it through FFmpeg to a dummy device, so it's way more stable in OBS. So I don't have to restart OBS or anything like that. So it feels way more nice this time. So I had some issues when trying to use my capture card last time. It was problematic, but yeah, it works better this time. Yeah, so I'm not exactly sure what we're gonna do today. So we can go to the GitHub and just have a look at the what's going on. So I created a bunch of issues with sort of big rocks to solve. Oh, hi, Triosomos. Nice to meet you. Welcome. So we're gonna look at something to work on today. If anyone has any idea for what I should look at, let me know and I can focus on that. But I was thinking of actually looking at the SRAM support, because that is sort of what turns the proof of concept into a useful thing, because you can save your save game. And that's also why I have Mario running. And yeah, as you can see, I have the original card here, so no piracy. And I want to sort of, one goal today would be to save in Mario and load it. That would be like a really cool goal if we can make that today. But to be honest, I am worried because the timing is faster on SRAM. So who knows? So yeah, I have no idea how it's gonna go. And we'll probably have to hook up the logic analyzer and look at the signals again. So it might be a little bit interesting in that way. Hi, Corgo. Nice to see you. Yes, I was just saying that we're gonna look at the SRAM, or at least try to use it. SM64 uses EPROM saves. Oh, that's good to know. That makes everything both easier and harder. That means we are gonna solder today, because let me show you the schematic. So you can see my screen good, right? Yeah, I have the camera. I can remove the cameras now, I guess. Or actually, let's have them there anyway. It's kind of fun. Something that moves. Also, I'm gonna move this a little bit, I guess. Yeah. So this is the Pico module. And the EPROM comes from these signals, right? So actually, I made a bug in this revision. This is the very first board I made. So this signal doesn't exist. This is only a label. I don't know where it comes from. I must have been confused or something. But these two signals, they map. Thanks for the follow, Triosmos. Yeah. Triosmos. Sorry. Yes, they go. The stat goes here somewhere. There's the clock anyway, and there's a stat. Those two and those two, they are connected. The thing is, though, I need to solder these solder bridges, but fortunately, that is very easy to do. Let me just show it in the 3D view. So we're gonna put two solder blobs here and here, and that will enable us to access those data pins through these GPIOs. So I'm not really sure what the best way is to do this, I guess. I mean, it's literally just making two solder blobs, so it's not gonna be very interesting. But we have some good test ROMs as well. So let me just open this. You don't really need SI clock 9. Oh, is it the same as the CIC clock? Let's see here. So is this essentially the same as this one? Or can I sort of sample it anyway and guess if there is data coming? Or I haven't looked at the protocol at all. I don't know anything about it. No, it's different. Okay. Yeah, so anyway, I think that might be interesting to look at today. So let me just find this test ROM. Here we go. Yeah, so this is a test ROM from Mick that is testing all of the sort of interesting things that are not the ROM. It's kind of similar to OneWire. Okay. So I'm curious, have you implemented this, Corva, in the summer cart? Because then we could look at your HDL, I guess. Let's think a bit, where could that code be? I've done it in FPGA. Okay, but that's good. All right, it's in a different repo, right? Or am I just being blind? Because this is the repo, right? Maybe. Okay, here we go. I was confused by the firmware name. Okay. Could it be here somewhere, perhaps? Okay, you even have Flash RAM. Cool. Check latest branch. Okay, we'll do that. And also, let me just check out this code. Now I guess I can turn off the cameras. It's not that interesting right now. And let's switch to another screen. Okay, so this is the actual memory, like physically. So the actual SRAM, actual flash, and so on. It's all in N64SI. Right, serial interface. Makes sense. Didn't use my brain. This is not that much. Interesting. So what do we have? We have clock and the data and the reset. And then I don't really understand system Verilog that well, but I guess this is an instance of SCB, which is this file. Oh, wow, what is this? Lots of stuff. So is this sort of the larger module that does everything, or? Okay, so you can access the actual flash RAM through this, I guess. So from the serial interface, you're accessing this. It's just bundled wires between modules. Okay, cool. So this is like a shift register, I guess. And this one is on the DQ rising edge. Okay. Yeah, I need to warm up. It's byte oriented with one stop bit at the end. So it's kinda like UART-ish. Is there a start bit as well? Maybe, are there any signal captures that we can find online? I guess on the N64 Brew wiki, maybe it's documented. Because I'm totally green on, oh shit, the SI. I'm totally green on the serial interface. I haven't looked at it at all. So this is more about the registers and stuff. But yeah, I mean, all the truth is here in the code, so we can. You're more interested in Joybus protocol, okay? So that starts here. Joybus address, sub address, full address. Okay. And then the EPROM controller. Okay, so and this is what we're gonna emulate, right? We want to become an EPROM. And it's only 2 kilobytes, right? A byte and then 2048. Yeah, this looks pretty simple. Where does the command come from? Okay. Oh boy, coding time. Yeah, so just to explain what we're doing, we want to implement the EPROM over the serial interface in order to be able to load and save games. For example, Super Mario 64. But I have no idea if we're gonna succeed, to be honest. It's, yeah, it might be a little bit complicated, more complicated than I thought. Because it's a serial interface and we need to, first byte is always command. Okay, good to know. So, yeah, right, so this is the state machine for your received idle data. And then rx state, it's idle, command, otherwise it's data. And then it just keeps that's right. I wish you the best of luck. Thank you. Right. All right. So, yeah, I don't know. To be honest, I was thinking, to be completely honest, that SRAM might be a little bit easier. The only problem with the SRAM is that we need to be fast, which is a little bit of a problem, but not impossible. So if we just go back to the code here, I did some performance measurements on my horrible project with flying wires, so horrible signal integrity. So that probably explains why why it failed at higher speeds. And now I have a soldered unit, which is a little bit more in a better state. I have a ground plane, it's 4-layer board, and so on. So if we try to overclock this, it might actually work much better, I think. So yeah, I don't know really. It's really hard with the streams, like what you should focus on or not. Okay, check this. Thank you. Okay. So it's a proprietary non-standard serial protocol, which the N64 serial interface communicates with controllers, controller accessories. Okay. So there's always like the start, it always goes down for at least one clock length, and then we have these different. Yeah. Thanks for the follow, Sharpiro X. By the way, have you fixed first board or just picked a fresh one? So to be completely honest, I have one PCB that I'm gonna scrap. But fortunately enough, JLC are nice, so they sent me 12 boards, and I only have 10 SD card connectors, so I'm okay. I'm okay. So yes, to be honest, I mean, I didn't throw away the FlexiPens. I ripped them out and soldered them into another board, and that works completely fine. But yes, the first attempt at soldering FlexiPens failed because I was being stupid. Yeah, I basically soldered down the flexiness of the FlexiPens, so that was very stupid. Don't do that. So if you want to learn from my mistake, let me show you the picture. I posted it in the Discord somewhere. Let me see. Yeah, here we have it. So yeah, don't do this. So in order to explain what's going on in this picture is two different things. First of all, as you can see, these pins are upside down. Yeah, I don't know what happened in my brain. Oh, you have a link to the Discord? Yes, I have. Okay, the bot is dead. The bot should post a link to the Discord every now and then. Let me see if I can fix the bot. Here we go. I mean, I can post the link, but I think it would be nice to just have. It's supposed to be Discord. Here, there. Okay, it was just slow. Cool. Yeah, so feel free to join. Yeah, so to explain what's going on here, two things. One, I have soldered. You're supposed to only solder this outer pin, and then here is like an open slot. So flexi pins. So you see this shape here. So this is the part that you should solder, and then this part you should not solder, because if you look at the PCB, it's easier here. Yeah. So the short part goes here, and then the long part goes here. And these holes are for people who want to solder 0.1 inch headers instead. So yeah, it's quite flexible, so to say. But anyway, so the mistake, I did two mistakes. One was to solder this part. The other was obviously to solder these upside down. So yeah, shit happens. The problem is I tried to wick up all of this extra solder, which took a good while. But the problem is that when you solder down other things, this sort of solder, because I'm using leaded solder, it melts quite easily. So it's really easy to get the FlexiPin to yeah, melt and stick, which is not so nice. So I ended up scrapping this card, but I saved the connector, so at least that part is good. Yep. Okay, so Joy Bus, what more? So 0, 1, console stop and controller stop. Okay. Stop bits are 4 microseconds long, while console stop bits is 3 microseconds. Okay. Does it say something about the clock? Like, is the clock on these lines? I mean, we can of course read all of the documentation, but if the clock is like going positive edge here or negative edge here, or if it's going here, like in between. Is there much headroom left on the Pico? Is there enough cycles left to run code that alters the ROM in real time? CraftLab. So yeah, about that. It's a little bit complicated. We have these timings. Maybe I should make it a little bit bigger. There is no clock. It works like one wire. Okay, so there is really no wire, no clock. Okay. So I need to sort of measure the time. No, wait a minute. That wasn't. How do we get the byte? We get the byte. Here, like a shift register on the positive edge of clock and RX bit valid. So which clock is being used here? Is it system clock? Okay, so that is the system clock. And what determines RX bit value? It is the DQ rising edge. Need to stop for a meeting. Okay, thanks. See you around. If CIC can be replaced with a tiny 3.3 microcontroller, that frees a whole other core. Yeah, that's true. That's definitely true. The problem is the latency, that we want to sort of we get an address and we want to reply with some patched data, I guess, immediately. So the cycle, sort of what happens between getting an address and outputting a bit that is, with the current implementation, this is the limitation, 240 nanoseconds. And this is just outputting static data, and this is outputting data from Flash. So essentially what's happening is that in C code here, we get the address here, and yeah, if the address is something, we save the address, and already here you could sort of do your patching or stuff. You could yeah, actually, now that I look at this is stupid. I should, or no, or yeah, I should move this up here. Oh no, right, that doesn't work later on. I was thinking of prefetching the data. Yeah, the problem is that when you read more than just one word, we're gonna stay in this state. But it might help with prefetching from the cache, or prefetching it into the cache. So anyway, you get an address, and then you have to present data, which you do by reading and then writing it to the PIO. So here you would do your patching or whatever you want to do. And yeah, I don't know really how much you have to, like, how much processing power you need, how many clock cycles you need in order to do whatever you want to do. But if you want to do like cheat stuff, I don't really know how that works. Thanks for the follow, Dur512. Yeah. So anyway, this is where you would put the patching, so you can experiment with that. One way to get around this sort of limitation, or expand the window of time, is by patching this. So this is the first word that we're loading when booting. It configures the bus, how much time we're gonna spend. Yeah, how much time we have until having to present correct data, essentially. So right now it's configured with a very biggest time, largest time, and even then Mario boots. So yeah, of course the original SDK provided value is this one, which is quite fast. But yeah, anyway, even in my FPGA cart, I fetch data right after address latching and fill in a 4x16-bit FIFO without knowing if it's read or write transaction. Yeah, that makes sense. That makes sense. So I guess I could, yeah, PIO has some FIFO, so maybe use it in a similar way. Yeah, I thought about that. The problem is that I need to flush the FIFO as well, in case, yeah, because I'm using the same FIFO for sort of the address and data request. It might, I mean, I'm sure it can be optimized, because we wrote that during a stream, and it sort of, we went with the first implementation that we came up with, and it's in no way the best. It works, but I'm sure we can do this better. Like, here's the synchronous sort of stall. We, at this point, we know that we have a read, so the read signal went low, then we push an empty message, which corresponds to this block. And then we pull, which corresponds to this. Oh, sorry, actually, this is not true. We end up here. And then we wait for something to come from the C code. So already here, yeah, this can be done better, I guess. And also we can do the auto push stuff. So we save a cycle. That way this will be faster. But yeah, it's a bunch of stuff we can do for sure. Yeah. So I guess just to get started with this, I guess we can load up, where was it again? Here, this one. Apologies if it's already been asked. Can this run fast enough to read the data from Flash, or does it have to hold everything in RAM? Yeah, so just to give you an example, let me show you. So here's the N64, and I turn it on, and reboot Super Mario 64. And it runs live from the external flash, and nothing fancy. Very impressive hack. Thanks. I've been reading about PIO documentation, and I think you can split PIO program into 3 separate parts running on different state machines. One for address latching, second for reading, and last for writing. Yeah, that's true. That's true. I haven't really thought about that because it felt too complicated for my head to sort of grasp what is going on. But you're totally right. So the sort of code that I've seen that does this is like the SPI core, where you use the pins that can be different between the state machines to sort of be multiple instances of the same thing. But in our case, we could actually do multiple things with the same PIO block. And actually, maybe we shouldn't go that route. I'm just thinking we have actually 2 PIOs, so we might be able to do something with the second PIO as well. Thanks for the follow, Stretch Dude. So yeah, if we stick with 1 PIO, that would of course be ideal. Let's go here. So just having a look at the code again. Yeah, I'm sure there's a better way, but we could count the number of instructions. So let's just count a little bit. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's only 21 instructions, and we have 32, and we can already remove 1. So we're basically down at 20 instructions. So we have 12 more instructions, which we need to use in order to detect the write and something else. So yeah, but PIO is still a little bit scary for me to do the creative stuff with. But I guess it's an option for later. Maybe we have a different entry point, or we set the X variable or Y variable to something, and based on that we can branch differently. So one state machine waits for the what's it called again, write, and one waits for the read, stuff like that. So I guess the write state machine would be able to run completely in parallel because it doesn't change the what's it called again? The output state. Where do we do that again? The pinders, yeah. Because we don't want to mess with the pinders from different state machines, because we might end up in a strange state where 2 things are trying to do. I mean, we wouldn't want to end up there anyway, because you only want one state machine to be in an active state at one time, I guess. But anyway, that's a really cool idea, and we should definitely get back to that later. So I was thinking of just expanding on this logic here, where we wait for the read, and sort of add something here where we wait for the write. But essentially, that will add a lot of instructions. So yeah, it's a really good idea to put that in a different state machine for sure. For sure. Yeah, because one other thing with the state machines is that I sort of expected you to have to use this sort of variable pin configuration thing where you can have different pins in different state machines. But in our case, we don't really need that. We could, I mean, essentially, we could just have the same program and just do more things in parallel. So anyway, yeah, really cool idea. Let's get back to that later. Yeah, so I was gonna look at this test ROM. So let's check it out. Nice. Okay, so let's run this on the console. Obviously, it's gonna fail, but I think it will be good to sort of have it up and running. So let's think a little bit here. Yeah, just 1 second. So we can do it like this. Then right now this is kind of manual. I'll add a script soon, but right now we have to change this prototype for the ROM in order to tell the linker to put it in Flash and not copy it to RAM. Then we build it. Let me just find my one-liner. Yeah, here we go. So the state of the Pico DVI N64 output, yeah, I put that on the shelf for now because it was sort of a sidetrack that we just I don't know. It was an interesting thing to explore, but it's work in progress, and I think I might get back to that later. But right now, I think it's more fun to look at the I don't know, implementing the flashcard stuff, because I guess people are more eager to get that up and running. So let me just make this bigger. Here we go. So as you can see, everything failed, which is completely correct. We don't implement anything, but we can also run this test ROM. Now we know that we can run it, so that's pretty cool. So yeah, I don't know. I'm honestly slightly unsure which path to go on this stream. Like, should I solder these two jumper wire or solder bridges, and then we can look at the signals. So I will solder these two, which will give us these two wires into the N64. Right. Or actually, I guess I mean, what I didn't really understand was we're talking about one wire, but how do you measure the time? How do you measure the time of one and where did we have it again? These, yeah. You need some sort of time understanding to see a difference between these. So the PIO doesn't understand time, not unless we tell it to. Or I guess even you could use software for this because it's so slow. But I don't know. Now that I think about it, timer with input capture. Yeah. Yeah, that makes sense. So we have two cores, and one of the cores is running the CIC, and the other core is running the main loop for the cartridge. So I think we shouldn't mess with this core. This should have a dedicated sort of, it should only do this, nothing else. But the other core, which is doing the CIC stuff, is, yeah, doing the CIC stuff. But the code as it is written here does everything in sort of a synchronous way. So we get stuck waiting for clocks to go high and low. Question is, I think, Gorgo, you said something about that you had code that turned this into sort of a task, so you could actually do stuff and not block inside of this code. I guess if we want to mix this CIC code with the EPROM stuff, we sort of have to go that route so that we have two tasks essentially running, doing two different things at the same time. Now that I think about it, I don't really feel like writing that code right now. To rewrite this code into sort of a something that doesn't block. So yeah, it's an okay. That's perfect. That's perfect. So let's have a look. So was it this repo? Yeah. So now I'm still on this other branch, the LMX02 branch, LCMX02. Okay, so task set ready. Okay, so it has some sort of task. Where does that come from? Is that some RTOS? Oh, you have your own RTOS. Okay, cool. Which architecture is this, by the way? Okay, it says here Cortex M0. Okay, so it's actually compatible. I mean, it is M0 plus. Cool. It's a very simplistic RTOS. Okay, I mean, I like that. That sounds good. This does a lot of stuff. Well, yeah. But that means that I would need to sort of port your RTOS to the Pico, which I suppose might not even be an issue at all. But yeah, that's quite a significant software task, to be honest. So I think maybe I should look at the SRAM instead, because I kind of, yeah, I feel this is a little bit too difficult to do on stream. I will sort of just struggle a lot, I think. And it might be annoying to watch. I don't know. So maybe I should do the SRAM stuff instead. But at least now we have an understanding of the EPROM. And thanks a lot for the feedback and information in the chat. So I know what I have to do. So essentially, I need to make the CIC implementation into a task, and then have a different task doing the EPROM stuff, and then implement the Joybus protocol, which is very well documented, which is nice. But yeah, it feels like that's a little bit too hard for me to do right now. So let's shift our focus to the SRAM instead, because we already have a lot of that set up since before. I mean, we have the PIO stuff up and running for reads, so we have to adjust this into accepting a write as well. So I think I will do that. Otherwise, I think my head will explode if I try to do this on stream. Okay, so do we have a nice test ROM for writing stuff? So I know I can write my own test ROM, of course. But let's have a look at this code. Yeah, right, it's writing to the SRAM here, yeah. Okay, so this is the addresses, or no, the sizes. Address start, right. Yeah, it starts at 0x08 and then a bunch of zeros. Yeah. So let's just read the code a little bit and try to understand what it does. Cart main read. Yeah, okay, so it uses DMA to read and write from the uncached PI. Cool. So okay, so it writes a counter to the to some memory, and then it writes that to the SRAM, and then it reads it back and it compares the data. So really nothing strange. I was thinking we could sort of implement the read part first, which would be quite simple. So first of all, let's create some SRAM. So I think we should have it in 32-bit words. We just call it SRAM. And so the question was, how many bytes should it be, or how many words should it be? So it should be 128 kilobits, right? So divided by 32. That makes sense. So it's 4096 32-bit words. Does that make sense? Yeah, I think so. So there's our SRAM. So SRAM is 32 kilobytes in size. Ah, wasn't it? I got a little bit confused in the chat earlier today because the flash RAM is 128. Okay. Thanks for the correction. So it's even smaller. Okay. It's only, yeah, so it's only 4 kilo. Wait a minute. Oh, right, you're talking bytes. Yeah. Okay. Yeah, this makes sense. And there's one weird game that uses 3 SRAM chips for a total of 96 kilobytes. Do you know if they are back to back, like address-wise, that they were mapped in a sequential or contiguous manner? Because in that case, I mean, we have a lot of space, so no, there's some weird mapping. Oh, okay, thanks. Okay, let's begin here then. Okay. So what do we do? Well, essentially, we need to branch based on the address. So yes, we can just do it naively and do something like if last address and OX1. So we just check for some bits for a mask. So is this correct? Is this even correct? 1 second. I think I might. Feels like there is a 0 missing here. Isn't the PI domain, whatever it is, domain 2? Oh, here we go. It should be this one. Yeah. Okay. I just counted incorrectly. Okay, so it's fine. So I guess we should check like I don't know, the 2 most significant bytes, and that they should equal this. Or yeah, that's maybe not also. Getting anything done this week while SGDK is going on is tough. Yeah. Speedrunning. Hi, Bentamats, by the way. Okay, so already now I can feel that my brain is not very good. We want to match these bits and just make sure. Oh, thanks. Yeah. So I guess is it enough if we just check this bit is set? I guess. I mean, we don't really have to care about this last stuff, this unknown stuff. Let's just do like this. So essentially, if this bit is set, we are assuming that we want the domain 1 address 2. And then we just do the same thing over again, and we look for this one instead. Let's just put them in order. Yeah. And then we just write SRAM instead. Oh, done. Now we have SRAM read support. That was easy. Now we need to implement the writing. That is the issue. How do we do that? So I guess for this test ROM, we can have a look at how the timing is set up. So where do we initialize the second domain? Is that in the libdragon perhaps? Or do we actually do that? Let's just read the code and not guess anything. So yeah, let's just read the code. So display init, console init. I don't remember if console init does anything with the SRAM though, that domain. Card detect save type. Okay. Should we look at the libdragon code perhaps? Let me just find it 1 second. I have it somewhere. Right. So now we're just gonna read some code to understand how the SRAM domain is being set up. Here we go. Okay, it doesn't happen here. So I have a memory of that you have to initialize the SRAM PI stuff as well, but maybe that's not right. I just wanted to see like what the speed is the default. Maybe that's that happens somewhere else. I didn't go back and watch the whole VOD for the DVI mod. Did you hit any major roadblocks? Yes, I did. So essentially, for this stream, I kind of gave up and just went with the camera solution again. And so here we have the N64 being filmed with the webcam screen. And it's good enough. The thing is that the roadblock was essentially I was not able to sample data in a proper way. Like the data I got was always drifting a little bit. I missed some bit. I just got some bit errors essentially, which messes up the sync, and then everything looks horrible. Yeah. So today we're focusing on the SRAM instead, trying to implement the SRAM, reading and writing SRAM. Yeah, I don't know, maybe I should just stop looking at what I'm looking at. So I'm just trying to find the sort of initialization of the SRAM domain. So PIO couldn't handle the video input. Yeah, exactly. So, I mean, couldn't is not right. I wasn't able to do it. I'm still hopeful that it's possible to do. I just didn't figure out how to do it. Yeah, it would have been, yeah, I mean, it is really cool. And I still believe it's possible. It's just that I haven't figured it out. Yeah, sure, go ahead. If you want my code, I have it on GitHub. Let me show it to you. I can post a link. It's this one, and then this one. I'll just post it in the chat here. So, and it's it's the horrible code that we wrote on stream, but yeah, it is what it is. It's a starting point in case you want to give it a shot. Yeah. So I guess I probably will have a branch. Yeah, always check for branches. I mean, I like to work on branches in order to sort of separate experimental stuff from the main branch, but yeah. Okay, so maybe we should just write some code. Yeah, let's are you team main or master? I mean, main is nice. But yeah, it is what it is. At work, having a million CI jobs that go to the master branch and so on. Yeah, changing that stuff is a pain. It is what it is. But for new projects, I like main. It's more clear what it means. Okay, so let's do some yeah, what do I want to do here? I guess I want to read some stuff from the SRAM domain. So yeah, I want to do this. SRAM bank read. So let's just do this down here. And let's just read, I don't know, 32 bytes. Is this in bytes or words? Huh. I guess it's bytes. I don't know. Yeah. Right. Let's just read a little bit. And then let's do a very simple hex dump. Very simple. And yeah, I know this is really slow and bad, but it works. So we have the new line there. Yeah. So now we can actually see what we're doing. So let's create the build loop here. So we want to build and yeah. Okay. Yeah, now we should have that script. Now we should have that script, but I don't think we're gonna iterate on the code that much, to be honest. So let's just do this manual one last time. Famous last words. And we just patch this and we make clean. Here we go. And reboot. Okay, that didn't work at all. Did I mess up? So I should be able to read. Thanks for the follow, IOTCL. Yeah. Are you coding in TCL/TK? So let's just see if I broke something here. So oh, it could be my CIC changes. I mean the code in the C code here. That is wrong. Am I doing something wrong here, perhaps? Right, this is not good. I should actually mask this. This is always a little bit messy. Which bits do I actually care about? I mean, if we only care about, let's say, let me mask the MSB. Yeah. I've never played or read anything about N64. What are you trying to achieve? An emulator? Okay, so just a quick recap of what's going on here. I'm working on a flash cart, and that's bad. Let's go here instead. It looks like this. And we're currently implementing SRAM support for loading and saving. Yeah, that's about it. So it's using the Raspberry Pi Pico or RP2040 chip in order to achieve this. And it's yeah, it's kind of nice because it's very cheap and you can buy it. But I messed up my code here a little bit. N64 cart emulator. Yeah, that is correct. That is correct. So okay, so if we mask those bits and we only look at those bits, how much is that? That is a lot. Right, that is a lot. And for the cart, if we mask the same thing, and yeah, we got all of those bits. Right, I think I was trying to think too much before, which is always a bad idea. Shouldn't think too much. This is correct. Yeah. Okay, let's go. So just build again. What is the cart? The storage? Yeah, essentially, yeah. The fun part is it's more than yeah, it's storage as well. Can be a lot. So you have the ROM, the actual game, and then you have some memory, some persistent memory, and also some RAM memory sometimes. And right now we're implementing the RAM memory, the SRAM. Yeah, correct. Prehistoric. Okay, let's think. It's all the game process gets stored on the card as well. Sometimes it depends because of various limitations and yeah, reasons. Sometimes you have the game, the save games in your controller, like in a extra memory card that you put into your controller, and sometimes it's in the cart itself, and so on. It's a little bit. It depends on the game. is the long Pico board already getting replaced, or will the same stuff you're working on work on that as well? So it's actually the other way around. So this is the first PCB that I made, and this uses the RP2040 module, which has the advantage of breaking out every single GPIO. This makes it possible for us to work on this hardware to develop various features. In the previous stream, we made that other board, the PicoCart64 Lite, which uses a actual Raspberry Pi Pico module. But because that module is sort of limited, let's just show it. So the Raspberry Pi Pico doesn't have all of the GPIOs broken out. So we have only three GPIOs, which makes it not possible to. I mean, it limits us what we can do with it. But the pro is that you get this nice. Yeah, let's just render a little bit. Render. Yeah, there we go. You get this very extremely cheap solution where you have a 2-layer PCB, which costs basically nothing. And then you have the Raspberry Pi Pico, which costs $4, I think. And then you have this MOSFET, which is not strictly needed, which is a Jelly Bean thing for like, I don't know, 10 cents or something. So this is like a hyper cheap solution. The problem is that we're limited to the Pico, what it can do. So you have the GPIO limitations, but you also have the flash limitation. So this flash chip is only 2 megabytes, so you can't really do much with it. But you can, thanks for the follow, Marked Cram 20. Or is it Marked Cram? Anyway, so on the, it's only 2 megabytes of flash, but you can buy sort of third-party drop-in modules from AliExpress with 16 megabytes of flash, so you can run Mario and what's it called, James Bond, and some other little bit bigger games. Some RP2040 GPIOs used for Pico board internal needs. Yeah, that's true. So the Pico is yeah, it is simply different, but it is extremely cheap. And now just today or yesterday, I don't remember, or was it the day before yesterday? Anyway, Raspberry Pi, they released a Wi-Fi version of the Pico W, which will have a Wi-Fi module built in here. So that would be quite cool. That would essentially enable you to, yeah, load homebrew via Wi-Fi with a really cheap solution. Yeah, it was yesterday. Okay, hi Duke, by the way. Yeah, my time concept is really screwed up. I've been so much has been happening, and work and no sleep and stuff. But yeah, so that would be really cool, having a Wi-Fi Raspberry Pi Pico here, for sure. To be honest, I have a hard time seeing clones popping up with Wi-Fi modules that are competitively priced. Like the Raspberry Pi prices are so insanely low. Yeah, it's really an enabler. But yeah, for the clones, I don't know. But yeah, we'll see. So where were we? We were looking at the SRAM stuff. And also congratulations to winning that N64, Luke. Perfect. Yeah. All right, so we were looking at some bit masking here, and I was thinking incorrectly. Now we're masking on these bits, and we're essentially giving us yeah, a bunch of addressable space. So let's build this. Oh, actually, I think I flashed it. I lost track of what I was doing. Let's see. Okay, so let's just revert everything I did and start over. Because as usual, I was doing too many things at the same time. So now we have a new test ROM. We are exporting. Oh, right. Sorry. Change. So doesn't really matter. So we're flashing. Oh, actually, let me change the thing before. Let's just go back to the original code, which was like, oops, like this, I think. Oh, thanks for the Prime sub, Bin Avik. So, yeah, for a full card, there's twin RP. Oh, thanks, Kelly. That's really appreciated. Thanks for the sub. Okay, so now we've flashed, and let's see if it boots again. Good luck with the project. Can't wait to see what comes out of it. Ah, nice. Yeah, I mean, it just started. Okay, here we go. Now it boots again. So yeah, there are so many things we need to do. I made a couple of GitHub issues for like high-level investigative issues and so on. Yeah, but yeah, the work has just started, and there's a lot left to do. But I mean, it is feasible. We can boot Mario and so on. Now we just need to add features, and yeah, so that's what we're doing now. So changing to this should work, right? We're looking at these 2 bits that they are. Am I actually? Wait a second. Right, it's only 16 megabytes. So we should drop a couple of digits here. Maybe we do like this. Then we get 256 megabytes. Yeah, we will never support more than this anyway. So where did you learn to code, or where should I start if I want to go into that field? Oh, that's always a good question, of course, but I don't have a good answer. I'd say just explore things and be curious, and don't let anybody say that you shouldn't. I mean, shouldn't do X and Y. Just explore on your own. Be curious. There's so much information on the internet today. I guess it's easy to be overwhelmed, and it's hard to maybe find a starting point. But yeah, stay curious and keep exploring. But for me, my path has been long and strange, I guess. Or maybe not that strange, perhaps. But I've been, working with computers for as long as I can remember. Been tinkering and coding since I was small. Been working as a programmer my whole career. And the hardware stuff I've sort of picked up the last 5 or so years. Yeah. every person has a different path. Of course, you can go the education route, but yeah, it's hard to give a good answer. I've been doing a lot with hardware. Replaced the CPU on an N64 a few months ago. Wow, oh, that's a pretty difficult one, because it's quite big, that chip. If you don't know much at all and want to learn basics, there's a game called Human Resource Machine that's quite fun. Ah, yeah. Yeah, I mean, it teaches you concepts of computing, I guess, like how a processor works. Which I haven't tried it myself though, but I've heard it's good. So right now I guess I'm just not thinking straight. So why doesn't this work? Essentially, we want to mask addresses. So just to explain what I'm doing here, we want to check if an address should go here or there, and of course you can do stuff like larger than and less than, which might actually be fine to do because we're on a CPU, but yeah, maybe that's actually good enough. So we want to check the range, like are we hitting the external domain or the SRAM domain? So maybe we should actually do that. Yeah, I guess this is a case of premature optimization. We don't actually need to check for bits. So let's do like this. And go to documentation again and like this. Yeah, so thanks for the follow, Opossum5150. So yeah, let's just build this and see if it works. It really should work, because this is really naive. We're just, yeah, this should work. There's plenty of online resources, online courses. You'll need understanding of algorithms, how binary logic works, how CPUs work, basics of C language, assembly, binary code. Specifics are hidden in docs from CPU manufacturers. To make sense of them, you'll need the basics. Yeah, that's good. Good tips. There's like no upper limit of what you can learn. There's so much. Okay, now it boots again. So let's just go with this solution instead. So what you just observed is a case of premature optimization and not being able to think properly, so we just wasted time. So sometimes it's just better to write simple code, which is easy to understand, not try to do fancy stuff. Yeah, so let's do something fun here. Let's initialize the SRAM with yeah, something, I don't know. Something like this. And then we also need to update the program. So now we can put this back and rebuild the test ROM. Then we need to put it back here. Actually, when doing this style of initialization, you're actually creating a huge blob with zeros. So that's kind of stupid. Let's just fix that here instead. Let's just do like this instead. And I think we need to make it clean, because when changing the ROM header, sometimes it doesn't bite. The beauty of software is in its forgiveness. It's a field where you can screw up with a few consequences. So go for it. Try things and break things. You'll learn a ton. Yeah, that's really true. With PCBs and hardware, not so much. It might blow up. So software is nice in that regard. Yeah, you should do something that motivates you. Make it fun. Makes it fun. Don't try to take everything at once. It gets frustrating and demotivates. Yeah, that's really, really good tip. I think you should always strive to understand the software you write, even if you're copy-pasting from a tutorial. Yeah, that's easier said than done sometimes, though. But yeah, definitely strive to do that. Okay. So yeah, check it out. We have our ABCD. So our SRAM read works in libdragon. I don't really know which timings we have here. But yeah, this is a step in the right direction. So just to explain what you are seeing is that in our code, we are copying this string ABCD, which in hex is 41, 42, 43, 44. And we put that into the SRAM memory. And then here we map this memory area. So when the N64 is asking for a memory in this region, it is loaded from the SRAM memory buffer. Yeah, for embedded, you have the magic smoke. Yeah, definitely true. Embedded is closer to hardware, so if you screw up, you could actually blow up stuff. So it smokes. Yep. Okay, so let's implement write. How do we do that? So I guess we will go to the test ROM, and yeah, let's just read 16 instead, because we don't need that much. So let's do this. So we need to invalidate and write. Yeah. Okay. So we need another buffer for writing. And I guess we can do something similar. We just copy a string. Let's copy hello. Perfect. And then we write it, but then we also need to read it back. So we're gonna do this one more time. Like so. Yep. Open the wrong circuit, mains voltage. Oh shit. yeah, don't do that. Like a serious piece of advice: be really careful with mains voltage. Like if you maybe look on YouTube or whatever and see someone experience the poke around without being careful, just don't do that. It's dangerous. Yeah, I don't touch anything above 12 volt. I think that's scary. 24, it already starts to be a little bit dangerous, but it's still okay. As far as I'm concerned, 3.3 volt is high voltage. Yeah, you're right. 5 volt is already a little bit scary. Yeah. Okay, so I think the, oops. There we go. I've been electrocuted so many times, I can't feel anything under 24 volt. Well, yeah. I melted my metal spudger once whilst attempting to repair N64 power supplies and shorting the caps out and having forgotten to pull the plug. I mean, I'm glad you're alive. Under 50 volt DC is fairly safe. Adjust everything below 30 volt. Yeah, I agree. I think that's a healthy spot. Yeah, yeah. I agree. But yeah, personally, I don't want to touch anything above 24. That's just no fun. Okay. So the reason why we see the 41, 42, 43, 44 is a little bit curious. Let's look at the code again. Did I mess up something? So the read buff. Right. Because we are actually reading. Yeah. This is correct. So yeah, what we're seeing is essentially that the SRAM it stays the same. It is still the stuff that we initialized it with, which is correct because we haven't implemented writing yet. So let's implement writing in the naive way, which is to add logic here. So essentially what we're doing here is we are waiting for something to happen. Either we're waiting for the pin, the assigned pin, special jump pin, which is the ALEH, to go high. When that happens, the bus transfer is done. So that is what this jump does. The second thing we want to do is we need to read GPIO 19, and that is the read pin. And if that is low, we continue. But if it's high, we loop. So the question is, thanks for the follow. Thank you, Toot. So one way to solve this is, because Luke is here, I kind of feel a little bit, I'm gonna write something so bad and inefficient here. But anyway, one way to do it is to add some extra reading a bit and jump logic. Alternatively, we do something fancy, but I think we should start, because Korgo mentioned earlier on the stream that we could do the state machine stuff and do like multiple things in the same program at the same time and stuff like that. But let's start easy. Let's start simple. So essentially, we need to do read or check if N64 limit right goes low. So in this case, we need inverted logic, which is a little bit annoying, I think, because this is sort of a follow through thing. So if the read pin, which we are getting here, and loading it into X. Oh, we could do something smart here. We could do something really smart here. Because the pins are adjacent. We have the write on pin 18, and then we have the read on pin 19. We could actually do 18 bits here, and then read 1 bit into Y, and then we just read 1 more bit into X. So now we have X and Y. So Y is write, and this one is read. Oh, thanks for the Prime sub. That's really appreciated. Thank you to it. Yep, thanks a lot. Okay, so what do we do now? Now we have 2 registers, one with the write and one with the read. Here we branch on read. So if we are not reading, we're gonna continue. So should we do something smart here? How do we branch on multiple things? So essentially, if we want to branch on a low, so let's look at the documentation for the PIO, and don't worry about spamming in the chat. Like, really, feel free to write as much as you want, because we are so few. So just keep writing. It makes it interesting. So yeah, let's look at the RP2040 PDF and look at the documentation for PIO jump. So what can jump do? It has a condition. X minus minus. Oh, you can do scratch 0 as well. Yes. Perfect. Let's do that. So if not Y, go to handle right, essentially. And so now we need to implement this thing. We might be able to reuse some of this, but no, actually. Let's think. Because we are writing data, what if we write a 0? That's gonna be an issue. Because we have this logic here where we send the word, the address, and if it's a 0, we do this loop, but if it's not a 0, we do that. That will be an issue for sure. So that means we need to be stateful. So this part of the program needs to know, oh, we started a read. So maybe we should encode reading and writing in the address. Like if we set the LSB high or low. That's, I don't know. Need to think a little bit here. Like how do we actually handle a write? Because in the read path, what we're doing is that we are pushing a 0 which acts as a command to request data. So when the address is 0, we're ending up here. And then we're pulling. And then we're looping, waiting for the next read. But in this case, we are waiting for a write. And when we get the write, what do we do? Well, we don't need to request data, but we need to push I need to think a little bit here. Let's look at my own FPGA card and just look how I did it here. So because it's an FPGA, I can do so much more, and I don't have any limitations. But yeah, for writes, I'm simply looking at if the write is low, I enter the writing state. I latch the data. Let's see here. So the data to be written is being latched, right? So when the write signal goes down, that is when I should latch the address and data, the AD pins, and interpret them as data. Yeah. So essentially, just to write this code, we let's write the label here. So here we should do the in. Right, because we can only read 16 pins at a time, we could actually encode stuff in the LSB. That's actually not a bad idea. Then we don't need to be stateful in the C code. So yeah, we sample, put it into the pins, yeah. But then we just immediately we want to put stuff into the pins. Let's think here. Because if I just push now, it will be a lot of zeros and stuff in the MSB part. So I could do stuff like in or how do I do this again? I want to shift in like 1 bit. Or do I? I'm not really sure if what I'm thinking is a good idea or not. But just to like, if I just have it like this, what is going to happen is that we're going to sample the pins. And we're going to push this as a word. So we're going to end up here. And this will not be true, but we will have a lot of zeros. So I'm thinking, can we encode a 1? We could do that by doing in. Let's look at the documentation for in. So source, we have pins, we have X, and we have Y. This is good because X and Y is, you know, a scratch register, which is a 1. This is only pushing 16 bits on read. Yeah, correct. So just to reiterate my issue is that we have only one communication channel. And if I send all zeros, then I have this logic which, like if it's all zeros, then I'm interpreting the action as a read and also incrementing the address. But if it is something else, then I interpret it as a address. But in this case, we're sending data, which can be both 0 and all FFFF and whatever. So maybe we should check something like, because addresses are always aligned, so we could do something like if address and 1, that means we gotta write, for example, and then data is shifting like so, perhaps, so that essentially we have so in this case, for example, these are the actual data bits, and then here we have encoded the LSB to be 1, so that we hit this branch. And then here we have a 16-bit word. I think this might work. I mean, it will be a little bit inefficient, but we need to figure out how to get this one here. So I guess one way to do that is to, let's see, so encode 1 in LSB is to do in wait a minute, yeah, move ISR not null, and then we need to shift out 15 bits of zeros. How do we do that? I mean, essentially, just to explain what I'm trying to do, I need to get a 1 here. Then I need to fill this with a bunch of zeros, but only 15 of them. And then we want the actual data. So while shifting, it will sort of look like like this. We're shifting in a 1, and then 15 zeros, and then the actual bits. So these are not actually ones, but like the data we want. But we want to shift in this word essentially. So I'm trying to figure out how to do that. So what this does, it turns everything into ones. And then by using in pins, I'm actually sampling data, but maybe I can do in 0 or something. Let's see what I could do. In X, right? Because here I'm using move, right? So I could do in, let's think. Yeah. This is right. So shift in 15 zeros. And then we sample it. But the problem is now this will happen 2 clock cycles later, which is not ideal with SRAM because here we need speed. But it might work. So then wrap, but we should actually go to this one. So instead of jumping there, let's just move the wrap target there. Sounds appropriate. I was starting to look at RQ to handle writes, but that would disrupt the processing on the CPU side and probably also waste a good bunch of CPU cycles. Yeah. Good thinking. But yeah, I'm also worried about the context switch stuff. I don't know exactly how interrupts work, how much they cost. We haven't really measured that yet. I'm sure Luke knows, but yeah, I haven't dug into that yet. So the wrap target is there, but it doesn't have to be. All right, wrap target. Yeah. Wrap. Yeah. We want to go here actually. This is interesting. It's very experimental. I have no idea if this is gonna work, but let's try. So what is an interrupt? Okay. Good question. It's essentially a way to tell the CPU to execute some other code while you're executing code. So imagine you're here in a while loop. So the concept of a while loop is that you're running this piece of code, one line after each other, and then when we reach here, we go up here. But we are stuck in this loop, and nothing can really tell us to do anything else. An interrupt is a way to sort of break that execution, to do something not in parallel, but to be able to poke at us. Literally an interrupt. Like imagine you're reading a book and someone is poking at you. That's essentially what we're doing. So let's say you're here in the execution and you get an interrupt, then the CPU will jump into the interrupt handler, which is, for example, this piece of code. Then suddenly you're here. And then when you're done here, you return back to where you were. But those interrupts are not free. It costs time or like a couple of cycles to actually handle that. But it's a very effective way to do asynchronous stuff. Yeah. So for example, you're waiting for a button to be pressed. You don't have to like loop and check if the button is pressed all the time. You can handle it with an interrupt. So anyway, let's try to handle the actual write. So let's not do this and instead do SRAM address. Oh, not like that. Last address equals. This is just a very naive way, but this will help us be able to debug it because we will be able to see it quite clearly. And then continue tells us to go back to the loop. So I think this is a good start. Let's try it. I have no idea if it's gonna work or not, but we'll see. "10 to 15 cycles until first useful instruction." Okay. Yep. So it's still flashing. Flashing is not super fast on this, but yeah. Okay, let's see what happens. Okay, we did not write anything, so it seems that let's do this. Yeah, so it seems that this code did not trigger, but I'm not sure either. So maybe I'm not thinking correctly here. So we have a lot of ones. We shift in 15 zeros, and then we shift in 16 bits. So no, I think this is correct. It could be that we don't end up here, that there's a bug here. So why is the right pin. Since we're able to still boot, that means that this piece of code still works. And then because this piece of code still works, then this piece of code should work. Essentially, the right pin is stored in the Y register. So just to confirm with the PCB layout, we have write on pin GPIO 18, and then we have read on GPIO 19. So 18 and then plus 1, which is 19. And jump if not Y. Not Y means that Y should be 0. And that is exactly what we want to do. We want this signal to be low. So let's try something else. In this handler, let's just make an infinite loop just to see that we are actually ending up here. So what I'm doing now is I want to debug and set a breakpoint here. Essentially, I want to see, do we actually end up here? So in order to do that, I'm going to have this infinite loop. And having an infinite loop here means that subsequent reads should return 0. So in this case, we have, just to show you, we're actually getting 41, 42, 43, 44 the second time. So with this new code, we should get zeros on the second time. Yeah. So that's the experiment. Okay, still flashing up. Soon done. Here we go. Yeah, okay. This looks weird though. This looks weird. Right. Because this test ROM is doing a little bit too much, we will end up here too early. Right. So we need to change the test ROM a little bit. Was it here? Here. So let's just comment out this. So essentially, we only want this to happen. So first we read, then we write, then we read again. And then this one should be zeros, but this one should be correct. So let's try that. Okay. Yeah, for some reason it's a little bit slow to flash over SWD. When I flashed with the UF2 files, it was actually pretty fast. I think it might be the OpenOCD driver that's not optimal. Okay. Still looks broken. That is a little bit odd. So that implies that we end up here early. So let's just comment out this part. Try again. Yeah, sorry. So this part, we're commenting out the jumping to the handle right and just ignore that instead. Okay, so this experiment has shown us that we are taking this branch even when we are not writing. That worries me, because that shouldn't really happen. Unless libdragon is trying to write early, or I missed something in the main function. Debug init. Hello, JG Payroll. So I'm currently debugging why we seem to get a write request early. I'm still not really sure if that is actually happening or if it's just like a side effect of some strange code. Thanks for the follow, MTN Don't 1298. So we could hook up the logic analyzer and have a look at the signals. I think we should do that before trying to hunt ghosts. But it really looks as if, because it could be this debug init is viewer code that does some stuff with the writing to SRAM. Why the firmware is developed in C instead of MicroPython? Well, yeah, the biggest reason is we need speed, we need low latency, we need to be really close to the hardware. The other is that, yeah, C is, I mean, it's the right tool for this job, essentially. And we're not only doing C, we're also writing PIO, which is this assembly language, which is running in the GPIO. Yeah, I mean, it's a fair question, and I just want to answer it. MicroPython is a good tool for some types of problems, but this problem is not one of those. Yeah, sure, but we need this low latency loop where we are interfacing with the PIO very quickly. So it's not the right tool. MicroPython is good for many things, but not this. I think I will comment this one out. Yeah. But it's a fair question, and MicroPython has its place for sure. All right. Flashing. Okay, so this looks good. So just to speak a little bit about what we're seeing is that we're confirming that, yeah, so I commented out this debug init is viewer, because this seems to probe if you're like an emulator or if you're, if you have like one of those fancy flash cards. So I believe this one will write to the SRAM. So what we're seeing now is that, yes, we are reading something, we are writing something, and then we are reading something again. And the second time we're getting junk back. As you can see, we're not getting the expected stuff. And that confirms, let's see here, that that our branch is being taken. So I put this infinite loop here in order to sort of break stuff when this happens. So now we know that this works. We can comment this out. So now let's try to understand what we're doing here. Yeah, so we're shifting in all ones, and then we are shifting in 15 zeros and then 16 bits. So this doesn't look wrong, not in my eyes. So we should end up in this situation. And yes, it will look funny in the hex dump, but let's bear with me. And actually, let's do like this as well. Yeah. And yeah, this may overwrite memory and so on. Let's just not care about that right now. Let's just focus on, yeah, see if it works at all. Oh, right. Also, this will not work. We need to mask. This will not work. That's probably why it didn't work. We need to mask this because this address is actually pointing to 0x08 bazillion thingies. So yeah, we need to mask it. So, and actually now we can actually mask it to the size, which is this. But yeah, let's put a to do mask correctly. This is good enough for now. Yeah, and also we should shift this. Yeah, what is it? 2 or 1 places? 2, I guess. No, 1. Actually, let's not shift it for now. Or, yeah, this one should actually do plus equals 2. Yeah. So actually what we could do is to do something a little bit different. We could do like so. So we get a 16-bit pointer to the 32-bit word. Yeah, I think this is actually this. Yeah, and then this one needs to be shifted 16 bits as well, because we want to save these bits and we want to throw these bits away. Yeah, let's try this. what about the Copilot extension for VS Code? Don't you use it? Well, I tried it and it managed to, I was able to get Copilot to write NDA code from Nintendo. And I think that says a little bit everything about Copilot. I don't trust it. So no, I don't like it. I mean, they've trained it on basically everything. And they don't seem to care about licenses at all. I don't know. What if you use Copilot to write your code? Who owns the code? So anyway, I'm skeptical. It's a cool project. Don't get me wrong. It's cool, but I don't think I can use it. Okay, let's boot it. See what happens. Okay, this is bad. Yeah, they just trained it on all repos, even the ones that had licensing against it. Lol. Yeah, I mean it's a cluster. I don't know. it is. Yeah, it's in the terms of service. It's a curious tool, yes, and useful, sure, but legally, your call. Okay, so just to explain what we are seeing in the frame buffer here, we are reading back A, B, C, D again. That indicates that our writing did not happen. So just to try something else, let's always write 1, 2, 3, 4 on the first word or half word, and then in the second one we write address. Let's think here. Shifted 16 times, and then here we shift this one, or we just do like this. It will be ANDed, so it should be the one here. And then let's change the test ROM to only write, let's think a little bit. Oh, okay, so this is definitely a problem. I was writing way too much. So let's start with writing a little bit less. Let's write 4 instead. But we still want to read 16, so that's fine. So this will result in 2 16-bit writes. Yeah, let's try this. And let's go over here and if one couldn't understand what Copilot produces, there will be bugs as well. Oh yeah, for sure. I mean, it is cool, but I see it more like an art project more than like a actual productivity tool. But I mean, it is intriguing, but it's also limited in the usefulness. I'm not really sure. Yeah. But the funny thing is, like, if you start typing something that is like special, some special characters, it will just keep, dumping like NDA files and whatever. Imagine Copilot inserted code that is licensed. Yeah, I mean, yes. If you type like the Nintendo copyright header and just press tab, 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 it will just give you like files that it shouldn't have. Yeah, I'm not really sure. It seems kind of strange what's going on here. So just to reiterate what we're seeing here, we're seeing the same unchanged SRAM entry the second time after the read, after the write, which should happen here. So it is just as if this doesn't really happen, or it happens, but it something is slightly wrong. So maybe it is logic analyzer time. So yeah, I guess I will connect that one. So just give me a second to set it up. 1 second. Yeah, that's a good idea. We could try that, but I'm gonna wire up the logic analyzer, I think. Can you show on the screen which signals pretend to generate? Can you show like a timing diagram or data sheet? Yes, I can put that up on the screen. Just 1 second. It is this one. So this is for reading, but it is essentially the same thing for writing. It's just the write here instead, and then the write data will be valid here instead. Timings may be too tight. Yeah, okay. So let me connect the thingy. I think it might be the hardware default, to be honest, because I was searching a little bit in the code and I couldn't really find where it was being set up automatically. But yeah, we could try slowing down the timings and sort of verify that our code works and that the issue is the speed. It would be nice to sort of know that, of course. Almost done with it. Okay, now I need to look at this one that's here. So I need to flip this over. With F. Oh shit. So I'm looking at this from the backside, and we need these two signals, read and write, ALE-H and ALE-L. Okay, that's perfect. That's perfect. I'm just gonna connect those. And where do we have ground? I think ground is like up here. There we have ground. Okay. So ground is there. Then we have these 4 signals. Perfect. Yes, this was actually something like a bonus with the FlexiPins, that you get these kind of easy to grab on thingies, loops. The loops, you can sort of grab onto the loops. Yep, I think I've connected it. Yeah, 3 test points, exactly. That was actually my idea. And yeah, perfect. So just 1 second. Yeah, let's open up the application again. You can close this one. Okay. So let's reconfigure this. So what did we have again? We had read. We have write. And then we have ALEH and ALEL. And we want this one to be here, this one to be here, read and write. Yeah, perfect. All right, I need to connect it as well. I might have a little problem here. The USB cable is a little bit short. Okay, I'm gonna try if this works. No. Okay. Oh, it actually worked. Okay, cool. So I'm running the, what's it called again? SLI logic through a hub, which usually is kind of problematic. But it seems to actually work. So let's just configure this. Yes. And I guess we need 100 megasamples. So I guess we just start and run. Oh, it's already complaining. Okay. Wait, this looks odd. By the way, which hub in do you settle on? Hub, which hub? Can you explain more? Because I mean, I'm just using a random USB hub right now. But this doesn't look right. The read signal shouldn't be low like this. Everything is okay. This is odd. I think I might have shorted something, perhaps. We were looking for some decent hub last year. Oh, okay. Good point. Yeah, I think I'm using some Amazon that is decent. Yeah, it's decent. But to be honest, no, I haven't found like the ultimate USB hub. But yeah, it seems I have broken something, so I need to rewire stuff, I guess. Let's see. Strange. It is the oops. It is correctly wired up. Might be the board that was in a weird state, so let's reboot it. Weird. So now it seems broken, but I don't understand why. So I've connected the test points to this, and this. And I'm using this one as ground, which should be correct. Oh. I connected. So here's the thing with the Salai logic. I don't understand why they did it. But pin 0 is black and ground is black. So I connected pin 0 to ground instead of the other way around. Okay, I think my camera needs to cool down. I'm using a D800 as a camera, and its sensor gets quite warm when you have the live view. Yeah, let me just rewire this quickly. Okay. Here we go again. Let's try it. Reboot it. Okay, it started. So now we can measure it again. Yeah, this looks much better. Yeah, okay, now we have the full capture. Doesn't this look odd? Maybe I wired it incorrectly. Let me check again. Strange. Does Pico still need a whole Linux OS to run stuff? No. So it is a bare metal microcontroller. So just like a Arduino or STM32, just a raw microcontroller. So what we're looking at now is that yeah, I connected my logic analyzer to the bus, but I think this looks really messed up. But let's ignore that for now. But we see here that the right pin is going low a lot. Like a lot. And we're not writing this much. Something is wrong. This doesn't make any sense. Yeah, and it's 2-core, exactly. Okay, let's just look at this one again. We have read, write, LEH and LEL. But that doesn't match what we're seeing. I don't get this. I'm going to sleep now. I really like everything you do, and it annoys me not being able to collaborate more. From here on, just using the keyboard becomes boring. Greetings. Hey, I mean, I'm happy you were here, and hopefully you learned something. And yeah, let's see you next time. So, and also for the future, if you have more questions, just ask them. And there are no stupid questions, and I like to explain stuff. So just keep asking. Good night. Yeah. Okay, so I'm just looking at the oscilloscope here, the analog view, just to see if there is something weird going on here, but it seems to actually match reality. But so does the Pico, is the Pico fast enough to bit bang out signals for this project? Yeah, it's a good way to phrase it. It's essentially what we're doing, but we're not bit banging it with the CPU. We're using the PIO, which is this special yeah, state machine thingy that runs in a separate block. So it's this assembly language thingy where we do stuff with the bus. So this is performing the bit banging, so to say. And yes, it is fast enough. But what we're doing now is we're debugging why our SRAM write implementation doesn't work. And I connected my logic analyzer to the bus, but I must have done something wrong because these signals don't make sense. Like the LEH, it definitely has to go low, otherwise it wouldn't have worked. So I must have done something wrong. So let me disconnect it and connect everything again. So everything is connected up again. Let me just upload a photo. Put this on a post command. Okay.
Hey, in this video,
Sorry. Right. I think I have desktop audio enabled, so you probably heard all of that. But yeah, that's a good one. Labs. Let me put that exclamation mark PIO in 1 second. Cloudbot command, add command. There we go. So this is how I hooked it up. And yeah, it is correctly hooked up. And yeah, it's a little bit hard to see, but the ground is ground. Yeah, it is really 1, 2, 3, 4. So let's try again. Let's disable the analog part. It still looks weird. I really do not understand this, but maybe LEH never toggles. But it should. Don't understand this. So I switched it to the next bank. So let's do this as well. Rebooting. Okay. So essentially this should be the right signal. Oh, right. I mislabeled everything. Okay. Let's just forget about these labels and type read and then write, then maybe H and ADL. Right. Yeah, so this is correct. Oh. Okay. Yeah, now it makes sense. So now here we can see the write taking place. And we have two 16-bit writes, just as the code dictates. So the timing here is actually really conservative. We have 4096, which is a lot of time, compared to the read, which is also 4096. Isn't that like really? Oh yeah, because we use that bus timing. Yeah, remember we have this patch. We have this patch here. That is where we see those timings. Yep. So it seems that the SRAM in our case is using the same bus timings here, 4096. So this is extremely conservative. We should definitely have, that should be enough. Let's see if the camera works again. Okay, the camera is sad. I probably need to change batteries. That's what happens. Okay. So anyway, let's forget about the DSLR extra camera for now. At least we can see the N64 screen. So going back to the code, or actually let's make it full screen. So what we see here is that the SRAM contents is the same, even though we read it after we write it. We do the data cache write back invalidate. So it shouldn't be a caching issue. We could, there might be a bug inside PI that's doing read write after write. Yeah. So let's put a print here. Let's move the print here, which will give us some extra time. And try again. Good thinking. By the way, you had this FF Beauty all the time on the shelf. Maybe there's some Falcon Eyes pilot light as well. You know, in our hackerspace, we have these IKEA light panels, like they are like a big square. But I don't have those at home. And yes, I know I should get better lighting, but the problem is I don't really want to invest in my apartment right now because I'm moving quite soon. So I don't really want to buy lighting stuff because I'm gonna... anyway, maybe I should just get like a desk lamp. But yeah, the D800 is... I love that camera. It's really, really nice. But without light, there is nothing. So yeah, I should get better lighting. Let's see here. Light panels are okay if you manage to fix the flickering. That is a good point. But as long as, I can run the camera at the 1/60th for the shutter speed or 1/30th, should be fine. All right, I need to patch the this one. Like 160. Oh, okay. Yeah, actually, I don't have any idea how that works. But it gives really nice light. And if you saw on my... Yeah, you can show it on the stream here as well. 1 second. I just want to show a photo of the board. Here we go. So, can you guess what camera I used for this picture? Like, it looks pretty good, right? So the background is a light panel, and then above I have another light panel. And I didn't spend any effort on this. I just turned on the lights and snapped the photo with my iPhone. Yeah, correct. And it's all about light, because it looks, I mean, it looks really good. But with good light comes good photos. And then here at home, I have shit lighting. Yeah, it is an iPhone. Yeah, the weird ones with the letter R something. XR, I think. Anyway. Where were we? Did I flash it? I think I did. So we're ready for another test. Okay, same as before. So maybe there's a bug in the code. I'm writing to write buff. I mean, I write with write buff. I do a string copy hello, oops, into write buff. This is correct. Like sometimes I manage to do the stupidest bugs, but this actually looks correct, right? We have the buffer there. We do a string copy into it. We invalidate the buffer, which I guess shouldn't be needed, but anyway. And then we write this. Bank 0, offset 0, length 4. We can increase this to say 16, I guess. And then let's just put some more stuff here, I guess. I don't know. Something like this. I guess -1 because it will copy a 0 byte. Now we are filling this with the 16 bytes of actual data, and we're using 16 here and 16 there. Cool. So this means we should see 8 transfers, I guess. All right. Okay, flashing is finished. Let's try it again. Okay. So it doesn't work at all. That's sad. It seems almost like we never end up in this branch. So I guess maybe we should put let's attach the debugger. How did we do that again? Yeah, let's do like this. And then I guess we need an OpenOCD as well. But instead of that, we just do init. And then we put a breakpoint in main.c line 43. Oh, it's not called main.c. I guess it's, I don't know, because I haven't built with debugging, maybe I can't even, that's annoying. I forgot how to build with debugging with CMake. I've done it once, but I forgot how to do it. So I still want the code to be optimized. Doesn't first if catch too much. Oh, that's a good point. Thank you. Thank you. Thank you a lot. Thank you. That, yes, you're absolutely correct. I think I could even do this already now. Yeah, you're definitely correct. Thanks, I'll keep that in mind. Okay, thanks. I want to like CMake, I'm just not used to using it. It is a great tool, but I'm just not used to it. Okay, and then we power cycle it. And show the camera. Okay, let's see what happens. This is exciting. Ah, damn it. Okay, so it didn't work. Let's do like this. Okay, let's take it easy, slowly. I'm checking for the LSB. Yeah. Yeah, I tend to agree. Like for packaging and so on, it's really nice. You just type CMake, dot, you know, type make and bam, it's done. But working with CMake, I don't know. I just never really gotten into it. Okay, but we check for this bit. Okay. Maybe I jumped the gun too early. Let's do this again. Yeah, I mean, make has its issues, but it's sort of quite direct. You write something and you understand what it does. With CMake, it's like lots of functionality. Okay. What am I doing? Restart it. Yeah. Okay, it's the same. What does this mean? This indicates that we never end up here. Because we should get the 1, 2, 3, 4 on the first word. And then hopefully we should have gotten the data here. But we didn't. I guess one way we can see if we end up here is to have a infinite loop. just to sort of well, thanks for the follow, Kaspas Donestas. So what I'm doing here is I'm adding this infinite while loop, which means that after we have written, the read that comes after should not work. So the expected data on the second SRAM read should be all zeros. If that happens, then that means that we have hit this code path. Make sense? So let's try. Okay, so this means that our write code path does not happen. We do not end up here. So that means that this stuff does not work. We could skip this so that everything is zeros. We also save one instruction that way. So just to explain what I'm doing here, when we get a write, we encode ISR with just full ones, just full ones, and then we shift in 16 bits of pin data. So when we end up here, instead of this, we will actually have yeah, let's write it here instead. So instead of this, it will look like this. What is adder? So do you mean, oh shit. I swap it. So, damn it. When I look at the one, it is not, it's in the wrong place. Yeah. Thanks. I think everybody realized the same thing at the same time. Thanks for pointing at that, JTH. So yeah, this is what I'm doing in the swap 16. So does that mean, oh no. So wait a second here. So I should check for this value here then, right? So essentially, yeah. Like this, right? Because swap 16, it just shuffles it around like so. And our one from the beginning is down here, and it will end up here. You can set shift direction for PIO. Yeah, that is true. That is true. But I think, yeah, right. So the reason why I need this is to organize the two 16-bit words in the correct order. Bitwise, they are in the right order, but 16-bit word-wise or half word-wise, they are in the wrong order. So I get like high, low, and I want low, high, I guess, or the other way around. So anyway, let's try with this. yeah, this looks really cursed. And this also means that we're gonna... Oh, this is not good at all. We're gonna hit this code path, I guess. Yeah, wait a second. I should do the other way around. Yeah, you're right. When reading the actual address, PIO program pushes 32 bits at once. Yeah. Yes. But I think I should do like this instead. So first we'll shift in the pins. And no, this is not good at all. Redeem hydrate. Oh, thanks. But actually, we can use we can do like this. So the Y register, if you remember from up here, will contain a 1 and only a 1. So by using NY16, we shift in 16 bits from the Y register, which will contain a 1. So this one ends up in the right place, I believe. So that way we can change this into that, I believe. Yeah, because that will be swapped. Yes. Just want to try the previous code that we had. And actually, thanks for the hydrate, because my drink is empty, so I should actually hydrate. Okay, let's just have a look. Okay, I think I broke it. Oops. Yeah, it looks broken. So I broke something. So yeah, let's just take a quick small break. I'll be back in just like 3 minutes. All right, I'm back. The bit order of the input data is not dependent on the shift direction. So when shifting 16 bits at once, their order should be maintained, I think. Okay. Yeah. But still, I broke something, so let's... Oh, right, because I have this while loop. Which means that we actually end up in this code path. Huh. Okay, we're onto something. So let's try again with removing the while loop. So we had the while loop in order to see if stuff broke, which it actually did. So we've sort of confirmed that we end up in this code path now. So now we just need to see if it works. It will be a little bit interesting. Starting the N64. Damn it. Okay. Well, it would have been too easy if it just worked. It didn't work. I'm gonna put the while loop back here again. Okay, so just to reiterate what we're doing. Without the while loop, we still got this, the 41, 42, 42, 43, 44, which indicates that everything is running, but it doesn't read the new data. We could also add UART logging, but that is sort of a little bit annoying to add, so I'm not gonna do that right now. Now I added back the while loop, which means that if the console, yeah, I'm not really sure what's gonna happen. We should get zeros, or it should crash, I don't know. Could be a caching issue as well. I'm gonna add UART prints. Let's just do that. We're gonna save some time. No, that is confusing. Yes, I totally agree. So I'm gonna connect here. So let's take it slowly and think a little bit. I have these UART pins here. So pin 28 is the one I want to use. Pin 20, no wait, GPIO 28. So this one. So it is PMod 3 that I'm gonna use. So looking at the board from my perspective, it is this one. So this pin I'm gonna connect to. Okay. I need some new jumper wires. Just 1 second. Oh wait, I can change the battery of the camera as well. Hello. And there we go. Yeah, without having to restart OBS. Fantastic. FFmpeg and Video for Linux makes it possible. So anyway, new wires coming. We need wires. Yep, looks correct. So let's guess be here. Okay. So either I connected something incorrectly or I forgot to do something here. I did this. Yurt is enabled. Oh, this seems wrong. That shouldn't really be there. But yeah, I should see this print. Okay. Let's flash it again. Okay, power cycling turning on, but nothing on the yurt. I probably connected something incorrectly. It should be this pin, which is, yeah, on the low side here. So it should be this pin. No, or yes. Oh, I don't know why yeah, it should be the number 3 pin, of course. There we go. Okay, so it is this pin. I don't know what I was thinking. Okay, should be fine now. Let's try it by power cycling. Yeah, here we go. So now we have logs, which means that we can put a log here as well. Right. So of course, after this print happens, we will be completely off timing wise, but that doesn't matter. We just want to see if this happens. All right, I should remove the cameras. There we go. So yeah, now I have connected stuff, so it's not that interesting there. So you can have more consoles, more terminals. Okay. So we did not get this print. That did not happen. So this never happens. Did we make a change to the program? Yeah, let's just build this one more time. Just in case we made some changes and forgot to update the ROM. So let's just update everything. We go here, we say copy, and yeah, at this point I should have made a script. And for every time I change the ROM, I will say the same thing. I'm sorry. Okay, so if this doesn't work, we could try. Yeah, we could fiddle around with the bits. But now we have a test setup. We have a print. We have a UART. We have everything. We have a logic analyzer. It's a dream debug setup. So that's perfect. Yeah. So power cycle. There we go. Keep an eye on the UART. Nothing. Okay. So what can we do? We can see if the MS, we can put the bit over there instead, right? So let's try this. So essentially instead of checking this bit, I'm checking that bit. Let's see if that works. And of course, yes, you could take it easy and really read the code and try to figure it out, but testing is, in my opinion, nicer. Okay, we got a lot of prints, way more than we expected. So, and this looks like the standard stuff. Yeah, right, which makes sense. Of course, yeah, this is natural. This makes sense. So let's fiddle around with the PIO instead. Instead of doing this, let's do something smarter. Maybe okay, let's do this instead. Oh, you can't do that. Okay. Let's I wonder if we can do this. I'm not really sure. Or if I should do the other way around, perhaps. I don't know if this changes the y variable when you do in. I think let's do like this instead. So my thinking here is that we sort of, yeah, this could have been a 0 as well, but the point is that the 1 should end up in sort of the MSB position. Oh man, this is probably some sort of alignment issue, or I mean like a byte order issue. So maybe it should be 8. Okay. Let's think a little bit. Essentially, I want to. Maybe I should put a sleep here before the write. Sleep for some time, and then log this. I don't know. I'm trying to figure out like what's an effective way to debug this in. I'm not really sure. All right, yeah, but I still want that. Yeah, but if we just think, so the default shifting was the shift directory direction. Let's just read up on that. So what is the default shift direction? Shift input register to the right. Data enters from the left. Okay, so just to illustrate what this means is that data enters from the left. Okay, so essentially that means that, let's say the shift register is only 8 bits left, 8 bits wide. So when we do in with a 1, this happens, and then in with a 0, then this happens, right? So that the bits travel in that direction. Shift input register to right. Data enters from left. And when we talk about left and right, do we mean that the rightmost bit is the so-called LSB? So this is a 1 and this is a 256. And just so we are clear about the bit order. I mean, it's the normal way to represent bits, but still. So in that case, that means that when we do this, that's what I understand too. Okay, correct. Good. So when we do this and we do, yeah, I mean, actually, when we do that, then, yeah, because AD0 becomes the LSB, right? This is AD0 and this is AD15, which also means that this should be the bit. Oh man, I'm so stupid. I'm so stupid. Oh, damn it. Y is of course a 0. Why? Because, okay, let me go through my code. So it's active low. When right goes low, we store a 0 into Y. But that also means that we cannot really use X. So I was thinking, can we use, I mean, I can just do do like this, right? Just encode a bunch of zeros. But that is illegal. Okay. Let's look at the documentation for PIO in and see what kind of sources we have. We have null, all zeros, and we cannot alter them. Okay. We have pins, we have X and Y. So I was thinking, okay, what if we use X? But is there a guarantee that X is 1 at this point? Not really, right? We can do not to. So I was trying that and I can't. But of course we can do move not null into, or which way was it again? Into Y. Then I can do this. Yeah, or we use X. It doesn't really matter. But yeah, we lose one instruction, but it will be good enough for testing. Let's try this. Okay, power cycling. Oh shit, it failed. Let's do it again. Okay. Power cycle. Oh, look at this. We actually got the rights. And it seems to be correct. Yeah, because it's A, B. Actually, this seems wrong. But we're on the right step. This seems to definitely sort of work. The question is, why do we get the same stuff here? And then we get the 3700. So this looks like we're writing. All right, let's do something better. Let's see. How many characters do we want? 16. So -1. Yep. There we have the part of the alphabet. We do make. We do the XSD stuff. We do the header stuff. And then I guess we are actually ready to do this instead. Yeah. So now it's getting a little bit exciting. I mean, we're getting somewhere because we can see this stuff in the logs. But what worries me is that it's the same thing, 31, 32 multiple times. That, in my opinion, doesn't make. Oh, okay. Oh, it's probably because the print messes with the timing. Yeah. Thanks. So let's just fix that immediately. Let's not even test it. But yeah, that's definitely likely issue. And let's double check the address. The address is in bytes. We're shifting the address one step so that we get the 16-bit address, and we set that to the MSB. Yeah, that looks correct. So, moment of truth. Here goes. Place your bets. What do you think? Will it work? Will it break? Turning on. Let's see what happens. Look at that. So it's still looks kind of weird. We get 61, 60, like it's byte swapped because of NDNS. But I don't understand why we get 62, 61, 62, 61. That almost feels like we get. Yeah, it is definitely progress. We're definitely getting somewhere. We have 6. It's almost like we have one word too much. Because we shouldn't get that many words. Because looking at the N64 code, which is here, we should get a null byte after this. So that's kind of odd. So the SRAM read seems to be correct, because when we read the stuff that is initialized in the CPU, we get the correct bytes. We get 41, 42, 43, 44. And looking at the code here, that is what it should be in byte order. So it is big endian byte for byte. 41, 42, 43, 44. As it should be. And then here we are starting to mess with sort of a 16-bit interpretation of the SRAM, right? That should be fine, but still. And then this one, yeah. What do we do? Take the address, mask it, we shift it to the right in order to get the 16-bit word address. I mean, this looks correct. Good. We are increasing the pointer. Yeah. Okay, thanks for transcribing it. That looks like we have a copy issue, that we're getting the same stuff twice. Why do we do that? Should this actually be like so? Looking at the PIO code again. Okay, what happens on the bus after the first 16 bits are written? Right pin goes high, then low again for the next 16 bits. Yeah. So let's make a new capture, because this is old and obsolete. So turning on the N64, and yeah, there we have the full capture. Showing the screen. Yeah. Oh, here we go. So here's the write, and here's the tiny read afterwards. So here's the write, and here's the read. So in this case, it actually does it only does 2 half words per transfer. That's kind of interesting. I would have expected the DMA approach to be this sort of, 256 write toggles per transfer. But yeah, in this case, it was only 2 half words per transfer. But anyway, write goes high, then the ALE H, and then ALE L. And then we do the whole dance again. So actually, it should look like this, I think. Yeah. And we do the whole dance again, and again, and again, and again. And then eventually, the bus goes idle. And then here, we start a new transfer, and this time it is a read. So here we read the data. Yeah, this is kind of quite short. This is the 224 nanoseconds of that we need to catch, but the PIO handles that. So let's actually do one more test. Instead of just writing this really short initial data, let's do 2 times. So now we have 8 bytes. Okay. So just to be sure that that stuff works. Okay, so let's remember that. Let's change this to actually do to operate at the 32-bit stuff, but still do the shift, just 1 shift. The purpose of this is to we should see 32-bit words for each 16-bit word. I want to see where the doubling happens. So let's start with this. So we're going to observe two things. One is to confirm that this works, that the SRAM initial data is actually being read out correctly. The second is that we are going to write to the 32-bit representation of SRAM with a 16-bit address. And actually, we shouldn't have to do that. We can actually remove that so that we get the whole. Anyway, it's done now. So let's just undo it so that we're actually seeing what we're testing. Yeah, so restarting. Okay, so this is actually interesting. This is interesting. As you can see, we see the 626100 and then 626100 again. That indicates that we're actually hitting this code path twice with the same data. We do that because we end up here. So is something wrong here? So we have the data, we have the null or the not null stuff. Yeah. Then we push. We end up here and we say, oh, address, this one is set. Yep, we do this stuff and we do continue. Then we do wrap. Wrap will do a go to automatically to the wrap target. And we end up here. Where should it wrap? Yeah, we're wrapping here to wait for another write or read, or ALH goes up. So this is the special single instruction if case. So actually let's improve on the pseudocode. Right? So if this one is 0, then we go there. Yeah. So now the pseudocode is updated and actually correct. So we wait for ALH to go high. And so if we look at the signals, we see that, yeah, write goes low, then write goes up, and we end up here. And then we wait for write to become low again, and that happens here. Oh shit, look at this. It's only 64 nanoseconds. It's very short, but yeah. And how long is it here? It's also 64 nanoseconds. Okay, so it is pretty short. Okay, but after that, we do another transfer, and then in which order does stuff happen? So first ALH goes up, then ALL. So we go to the wrap target, then we wait for ALH to go up. And if that happens, we go to card start, which is all the way up here. So at this point, we say, oh, ALH goes up. Yep, we go up here. And then we wait for ALH to go high again. So that happens immediately. And then we wait for ALL to go high. So we're gonna wait here until we get here. Okay, AL is high. So next one is we wait for ALH to go low, which happens here. So at this point, the address is latched. Okay. And then we wait for ALL, which is happening here. And when this happens, we're actually latching. Okay. Could this be an issue? Could this be an issue? Could we have junk? No, because we do 2 in. So having junk in the input shift register shouldn't matter, because here we do N16 and N16 again. And then we do push. Which should mean that we read 16 and we read up to 32, and then we do push at this point. And then we idle here until this happens. Right. And that looks correct, but why do we get it twice? I mean, I could hook up a few address AD signals so that we can see, what's it called again? The actual data. That way we could see a little bit more what is actually happening. So I guess I can do that. Let's take AD0 up to AD3 and connect that. So let me just turn on the camera again and yeah, let's restart the capture card because it kind of broke. The capture card is not friends with the Nikon. Think. Okay, here we go. Okay, time to connect some cables again. So this time, oops, need to connect some more cables. The annoying thing with these probes is that you need to sort of prepare them, but it's fine. I mean, it's not a big deal, but it takes a minute. It is what it is. Yeah, I really like the probes. I think they are really good. Don't have any issue with them. Okay, then we need a ground as well. Okay. Do we wait for right to go up after the first word? You know, I think you are onto something. Let's look at the code before probing. Or let's read the read. Yeah, look at this. We're missing this part. Thank you. You are absolutely correct. And instead of read, we do the write. Thank you. So let's build and try again. I think, yeah, that is most likely the bug. Yes. So, gonna power cycle soon. Ha, look at that. Thanks, Steve Mo. You hit the nail on the head. That was perfect. Thanks. Now it is actually working. And the reason why it's wrong is because I made it wrong. So let's make it right by doing two things. Turn that into the 16 and actually that's it. Now it should work. So thanks again, TFMO. You found the bug and we fixed it. Now we're gonna test it. Okay. power cycling. So this is it. Let's see what happens. Ah, look at that. So the only sort of odd thing is that it's byte swapped because of the big endian nature of the N64. So this is absolutely, let's think here. Is this correct? Or are we byte swapping it on the CPU? So let's do this twice. So let's do like this. Yeah. I'm not really sure if there is a bug or if there is not a bug, because I mean the whole endian stuff, I'm always getting so confused about that. It is really easy, but because it's so simple, it becomes hard. All right, you can't see my screen. Here we go. Yeah, Tifmo, thank you. Yeah, but you fixed the bug for us. Thanks a lot for that. You probably saved like another at least 15 minutes, half an hour or something. Definitely. So okay, let's look at the big screen. Right, okay, so what I just did, just to show you again in the code, I changed the N64 program to print out the string in byte order, and it goes in the correct direction. But then after we read stuff from the SRAM, it is flipped. So we need to unflip it. So the question is, should we flip it here? Or should we flip it here? I guess we should flip it here. Because now that I think about it, no, wait a minute, this is in the correct direction when we read it. We get 41, 42, 43, 44. So I guess we should flip it here. So we should do another flip function or a swap. So what do we call that? Byte swap. So it takes a 16-bit value and yeah, it turns. Aren't you doing byte swap for reads? So I'm thinking, oh, right, because I do that here. You're right. So, I mean, I could sort of, I mean, it's kind of nice to have like one implementation that does this. So I guess I should. I mean, by doing the byte swap here, when I save it, I don't have to have any special handling here. So I think I will go for that solution. So I will do the byte swap here. So swap 8 of this, and we do like so. Makes sense. Let's build and try. Can't really see. Oh, sorry. Damn it. So anyway, I made a very simple swap function here that turns this into that. and I perform the swap when I store the data in the SRAM. The reason for this is so that I don't have to do any special handling here. I want to do as few instructions as possible here. So I want to have like one common place where we do the byte swapping. And I guess ideally we don't actually want to do this at all later on. We don't want to do any byte swapping here, and instead do that somewhere else. Because we don't want to have, I mean, we want to have as few instructions as possible in this loop, I guess. And I suppose that also goes for the writes, but yeah, I don't know. I don't know really. Anyway, let's try this. Too much byte swapping. Yeah, I agree. I agree. If you byte swap at read, then the same thing should happen for write. Yeah. So anyway, let's just try this and sort of see. Okay, it works or not. Okay, it works. Good. So now we can optimize it. So now we want to get rid of this byte swap, right? So if we remove this byte swap, then we should also remove the byte swap here. So let's copy code instead then and do like this. And then for the SRAM, we don't do the byte swapping and just type word. And we don't really need to do the masking. Oh wait, we're gonna have a problem here. Wait a minute. The get MSB. Alright, because I told that here. Yeah, so next time we're gonna end up here. And then we need to do the byte swapping. Not byte swapping. I mean, I know I can byte swap the ROM, or half word swap the ROM. That way we will not need this. But let's just wait a minute. Let's just go back a little bit and make a commit here, because this actually works. Yeah. Yeah. And then like so. Yeah. So actually I'm gonna commit this now, I think. Hello. Yeah, right. So yeah, this is actually kind of clean. We haven't done any nasty stuff. All right, this comment doesn't make sense. Yeah. Test that it still works before commit. Yeah. Definitely. Okay, I think that is good enough. We have this one. We added this. Maybe I should move this up a little bit. Maybe here. Okay. Yeah, maybe I shouldn't have this. But let's just keep it there for now. Do another make. There's a warning. Because of the string copy, yeah, but we're gonna remove that before committing. Oh, hydrate, thanks. I have a full drink in front of me, but I honestly forgot to drink. Do we need to know which 16-bit word is being read? Some games require 16-bit alignment. the data from Flash should be read at 16-bit values. I'm trying to understand what you mean. I don't quite understand what you mean. Can you explain a bit more? Also, it's getting late, so maybe I'm just a little bit slow. Okay, it still seems to work. Currently, code assumes that read-write transaction is 4-byte aligned. That is true. That is true. That is perhaps a very stupid assumption. Just remove this one. Yeah, you mean because of this? But some games will not work with this assumption. Okay. So should we instead? Okay. So let's just make a commit. Let's just make a commit, and then we can improve. So implement basic SRAM support. Very basic SRAM support. Okay. So there we go. And then let's move this one up here and do like so instead. And let's remove that. So now it's way more correct, I suppose. Yeah. Yeah, right? This should be fine. Okay, good to know. So now this works on, and we can get rid of this get MSB then, because now we don't use that anymore. And this, right? It doesn't have to be static. My idea before with the static stuff was that I wanted to sort of prefetch stuff. Yeah. Oh, right. This is gonna be annoying. So we need something like this. And then now I'm not really sure which order. We're gonna get this one, and then this one, or the other way around, but let's just, I don't know. Let's think. Okay, actually we can use our brain. It should be this one first and then that one. So right, first that and then that. Yep. And then to get rid of the byte swapping, we can do so. And actually just write like so. And then do like this. And then here, we do the same thing. We don't want to do the byte swapping. But then in this case, we need to do the byte swapping. Swap 8. And then we shouldn't use the ROM file 32, but instead we need to do 16-bit access. Right? Makes sense. And then instead of shifting 2, we only shift 1. Same thing for the SRAM. And for the SRAM, we also want to do the SRAM on 16-bit accesses. Okay, do we believe in this? Maybe. There's a lot of changes, a lot of things that can go wrong. in the save, we should not do the swap. Okay, now I think I've done all my changes. So just to recap, I've broken up everything, so we are operating on 16-bit addresses. We are increasing the byte address pointer with 2 places, so 1 16-bit word per access. These 2 if cases are for the patching of the first 32-bit word, which is 8037 and then FF40. And we're not doing byte swapping. And then here for the SRAM stuff, we're accessing the 16-bit pointer. We're shifting with 1 position so that we turn the byte address into a 16-bit off-word address. And we do the same thing with the ROM, but here we need to do the swap, the byte swap. Okay, looks good. Time to try it. Okay, power cycle. Gonna turn on the camera. Oh, it booted and it's in the right order. All the changes worked. First try. That's... Oh, did you see that glitch? What was that? Let's restart. Could have been my webcam as well, I don't know. Or maybe it was just some video glitch. Yeah, I mean, it works. It works. And it's in the right order. Good, it's a bit cleaner. Yeah, I agree. I agree. Thanks for pushing me to clean it up. That's appreciated. And also for finding and fixing all my bugs. So, what do you say? Is it time to end the stream and sort of wrap it up? We've actually implemented SRAM support. Actual SRAM, because when you reboot, it's gone. So next step is to sort of make this persistent, store it in Flash somewhere. We shouldn't spend too much time on that because eventually we want that to be on an SD card. But yeah, great work. You have an amazing day. Thanks. Yeah, thanks for hanging out and helping me find bugs and encouraging me to to fix stuff. Yeah, it's been fun. Maybe try if save tester. Actually, yeah, let's do that. So I guess we can just push revert on everything. Actually, let me just stash instead. Stash 6D. Do the readme stuff. And for next time, I will have a script that does this boring thing for me. And we do the make clean. And this, yeah, you can see the camera there. Perfect. Good work. Thank you. So this is going to be a little bit exciting. Oh, right. We didn't have any memory protection. If you look at this code, we can sort of write basically anywhere in RAM. So yeah, it might crash. But let's try it anyway. So because we're limiting this to basically 256 megabytes or whatever it is. Anyway, let's try it. No. That's odd. That's actually quite odd. That's odd. I don't have any idea, and I guess I'm a little bit too tired to figure it out. But I think I'll come. I don't know. So actually, now that you're all here who kind of care about the project, the develop branch, in my opinion, is sort of it is the bleeding edge. This is where stuff happens. Things will be broken here sometimes and so on. But as users are growing and people are gonna get their hardware soon, we definitely need to sort of become more organized, I guess. So the question is the kind of state of my code here. I would say, okay, this is a good stepping stone. I'll just push it to develop and let's continue later. But, you know, is that a bad idea? Should I create a branch? What do you think? I mean, develop isn't stable. It is what it is. But still, it should work. It should, like, if you check it out and you run it, it should, you should be able to boot Mario, I guess. Anyway, doesn't matter. I'll clean stuff up later. Anyway, it was a little bit of a letdown to see no everywhere here. I'm not really sure why. I'll need to figure that out. What's scary is that people take it and try to use it as a finished product. Yeah, I agree, but I can't stop people. We could add more banners with blinking red, you know, sign point posts and like, do not try at home unless you know what you're doing. But people will still be like, yeah, it's fine. Maybe more consistent readme at first. Yeah. Yep. I mean, there is basically no readme today. It's just notes for myself. And the readme in the main repo was contributed, was very nice. And I guess we should build upon this and make it more clear what is actually going on. Do people read disclaimers? Yeah, you're right. People don't. Could also put something in the make file that just doesn't work and throws an error. Yeah, you know, that's good. For the Game & Watch project, I ended up adding so many fail safes so that, you know, in my opinion, it's really hard to do the wrong thing. But here, yeah, I'm not really sure. I'll figure something out. Contributed readme needs cleaning as well. Yeah, you're right. You are right. But documentation, it's no fun. But you're right. There are people who might, I don't know, expect too much or something. We need to lower the expectation of people by writing angry words or strong words, I guess. Okay, so I guess it's time to wrap it up. So again, a little bit sad to see all of the no's here, but it is what it is. But thanks again for everyone who hung out and helped me out. Really appreciated. So see you next time. And I'm always on the Discord. If you need anything or want to chat, just write something. I'll try to reply. And yeah, see you next time. Cheers.